Ladies and gentlemen, have you ever experienced the disappointment of being declined for a loan while others with similar attributes as yourself were approved? This discrepancy could be a result of bias present within the credit system. With the increasing reliance on machine learning, particularly in banking credit scoring, our research aims to assess and minimize bias within credit scoring machine learning models, ensuring fair treatment for all individuals and groups. My name is Shalem Mariska, and I feel so honored for the given opportunity to present our research titled Implementing and Analyzing Fairness in Banking Credit Scoring, conducted by me, Mr. Yoga Yustiawan, Mr. Fauzi Cesar, and Ma'am Epawati Tanua at the 7th ISICO 2023. Our presentation will cover these 4 sections. We try to assess bias with 2 fairness metrics, which are equalized odds difference and demographic parity difference. Mitigate the bias with 3 methods: pair processing, in-processing, and post-processing. By doing this, it promotes fairness and equal opportunities, ensuring that credit decisions are based on merit and financial behavior rather than demographic background. We use confusion matrix classification values as our base for the fairness metric to measure disparity. The true positive rate is the actual value that is correctly predicted as true. Meanwhile, the false positive rate is the proportion of actual negative values predicted as true. First, demographic parity requires that each subgroup has the same probability of positive outcomes. Secondly, equalized odds measures the true positive rate and false positive rate between subgroups to assess significant differences in the treatment of different subgroups. Both of these fairness matrix values are expected to be close to 0. A larger value indicates a higher level of disparity in outcomes, suggesting potential bias within the model. The first method to mitigate the bias is pair pre-processing, which means that the algorithm modifies the training data before being learned by the classifier. This pair impact remover algorithm works by changing the unprotected feature value to make the classifier more difficult to differentiate between the privileged and unprivileged group. The weighting algorithm calculates group-specific weights for each sample in the dataset. Underrepresented groups receive higher weights, amplifying their influence, while the overrepresented groups receive lower weights, reducing their impact. Fair in-processing algorithms act as the classifier to learn and mitigate bias in the classification process. Adversarial debiasing algorithm consists of 2 main components: a predictor network and an adversary network. The predictor network is responsible for making prediction on the target variable, while the adversary network tries to predict the protected attribute based on model's predictions. Metafair classifier considers the prediction of the base classifier and takes into account the fairness assessment results to make informed decisions. It uses a meta-level algorithm that combines the prediction from multiple classifiers while considering fairness considerations. Lastly, fair post-processing algorithm enhance the fairness of machine learning models' prediction after the model have been trained. The threshold optimizer algorithm aims to optimize the decision threshold of the model to achieve fairness. The decision threshold is the probability value above which an instance is classified as positive. By adjusting this threshold, the algorithm can control the trade-off between fairness and accuracy. Reduction method consists of 2 algorithms, exponential gradient and grid search algorithm. The algorithms adapt its prediction based on feedback received without assessing the sensitive feature. For our research, we use 2 datasets called the synthetic dataset and the public dataset from CapGirl that have 10,400 data and 30,200 data respectively. Our target feature is a binary classification, with 0 indicates not default or good class, and 1 for default class. Because our data contain more than 2 categories for each subgroup, we have to transform it into 2 groups, the privileged and unprivileged group. We perform calculation based on the amount of data in each category within the demographic features and the actual classification of the target features to get the positive probability. Those categories who are above the average of the positive probability will be classified as the privileged groups and vice versa. We use three tree-based algorithms to do the experiment with the hyperparameters tuning to maximize the performance. We split 80% of our data to be the training data and 20% for testing. To calculate the model's performance, we use the AUC value that is expected to be close to 1. Demographic parity difference and equalized odds difference are used to measure fairness, and a good result shown with value close to 0. The slide shows the DPD and EUD calculation results of our dataset. We choose to mitigate bias on feature A for the synthetic dataset and 6 feature for the public dataset. Here is the result after the mitigation. Baseline model means the unmitigated model. To demonstrate that the algorithm successfully improves fairness, the DPD and EOD values are smaller than the baseline model, while the AUC value remains closer to 1. With the pre-processing method, the disparate impact remover works with the random forest classifier for the synthetic dataset. Meanwhile, for the public dataset, it's better with the Rewege algorithm, although the EOD doesn't improve, but it maintains the performance. Next, the adversarial debiasing from fair in processing method performs great on both datasets, but there is a trade-off with the performance. Meta-fair classifier, on the other hand, seems can only handle the balanced dataset, which is the public dataset, but it doesn't give a good result on the EOD and AUC value. Lastly, results are quite varied for the post-processing algorithm. The threshold optimizer performs well for the public dataset, but only with the XGBoost classifier for the synthetic dataset. Similar results shown for the exponential gradient algorithm. The greatest algorithm can be beneficial if we are looking for better model performance. To be noted, the 0 values shown on the table do not mean that the results are completely fair. However, the algorithms fail to handle the imbalanced number of the dataset between good and bad subgroups. They learn more good class dataset and result in predicting all data classified as good class or the no default, which is not true. From this experiment, by improving fairness in the machine learning model, it can help to give more equality to the unprivileged group. Historically, the privileged group are more likely to get acceptance rather than the unprivileged group who also deserve. Enhancing fairness in our credit scoring models offers several benefits. Firstly, it ensures that applicants have equal chances of approval irrespective of their sensitive attributes. Secondly, it assists lenders in making more precise loan decisions. Lastly, it reduces the risk of defaults and unpaid loans. By improving fairness in credit scoring, we create greater opportunities for underprivileged individuals who should have access to loans without any consideration of their demographic characteristics. For improvement or further research, there are certain limitations that must be addressed in order to enhance fairness. Firstly, it is important for the algorithms to effectively handle imbalanced data. It is crucial to acknowledge that real-world dataset may often be unbalanced, with a larger number of data points for the majority class. Secondly, efforts should be made to minimize the trade-off between fairness metrics and the performance metric. Striking a balance between fairness and AUC is a challenge that needs to be addressed to ensure equitable outcomes. By addressing bias and discrimination within credit scoring machine learning models, we can promote equal opportunities for individuals and groups from all walks of life to access loans and financial resources. As we continue to advance in machine learning and algorithmic fairness, let us strive for continuous improvement in our credit scoring models to create a future where credit decisions are based on merit and financial well-being, rather than the demographic background. Together, we can build a better and more just financial landscape for everyone. Thank you.